In this video, we're going to go over Gay-Lussac's law, another one of the gas laws. But this time, rather than deal with pressure and volume, we're going to be looking at the temperature and the pressure and their relationship to each other. So let's go ahead and take a look at that relationship. So for Gay-Lussac's law, we're looking at a constant volume this time. So our volume will be staying the same. And we're looking at the relationship between temperature and pressure, and we can see that they're directly proportional to each other. So in other words, if we increase the temperature, the pressure will go in the same direction, it will go up. So as the temperature of a gas increases, the pressure increases and vice versa. Okay, so same direction. And remember, the amount and the volume of the gas are constant in this situation here. An example here is if we double the temperature, then you also double the pressure. So remember, if you recall that whenever you're dealing with temperature, it should be in Kelvin. So let's say we have 1 Kelvin over here, and the pressure is, let's say, 5. Okay, I'm just making those numbers up. If we double it, so this is 1, we double the temperature to 2 Kelvin, and we go measure this here, you'll notice that this is probably about 10. So we've doubled the temperature and therefore doubled the pressure as well. So what does the relationship look like, and what does the formula look like for Gay-Lussac's law? So we're basically looking at a relationship where the pressure is proportional to the temperature. So pressure is proportional to the temperature. And to represent that equation, to represent that mathematically, Gay-Lussac's law, we're going to use variables as we've seen in the other laws. So we're going to have P1, that's our initial pressure, over our T1, our initial temperature, is equal to P2 over T2. And it doesn't really matter what units of pressure we use as long as we're consistent. So whether it's ATM, kPa, PA, torr, doesn't really matter as long as it's consistent for both. But what does matter is the temperature we're using. So this is our initial temperature, initial temp. This is our final temperature. This is our final pressure. And this is our initial pressure. And as you can see, we have our graph over here as well. So let's go ahead and explain all this with the help of kinetic molecular theory. Why is it that when you increase temperature, the pressure increases as well? So pressure increases. And why is it that when you decrease the temperature, the pressure decreases? They go in the same direction. Right? So if you increase temperature, you've increased pressure. If you decrease temperature, you've decreased pressure. So when you increase pressure, that leads to greater kinetic energy. They're moving faster, there's more space between the particles, which means that the particles are colliding with the walls more frequently. So here we have a initial temperature and pressure. Temperature is 200 Kelvin, pressure is 1 atm, and they're hitting the wall, so they give us a pressure of 1 atm. But as soon as I double the temperature to 400 Kelvin, you'll notice that these are moving faster and hitting the walls more frequently, and as a result of that, the pressure has doubled as well. It went from 1 atm to 2 atm. If I went in the other direction, if I decrease the pressure, then the particles will have less kinetic energy, and so they'll have less space between the particles, which means they're not colliding with the wall as often, and so the pressure will go down. So if you half the temperature, then you've halved the pressure. But again, same direction. If you decrease temperature, you decrease pressure. And that's explained with the kinetic molecular theory. So let's try to practice a problem together. So we're going to determine the pressure change when a constant volume, so volume is constant here, of gas at 1 atm is heated from 20 degrees to 30 degrees Celsius. So first of all, let's write down some given information. We have a pressure 1 is equal to 1 atm. And this happens at temperature 1, which is 20.0 degrees Celsius. Now keep in mind, the reason I knew this is temperature 1 is because we're going from 20 to 30. So our new temperature that we're going to is 30.0 degrees Celsius. Now, before we move on, we need to make sure that we convert this into Kelvin. If we use the temperatures as degrees Celsius, we're not going to get the correct answer. So make sure you convert these to Kelvin. So plus 273.15 plus 273.15. So we can do we get 293.15 here, 293.15 Kelvin. And over here we get 303.15 Kelvin, 303.15 Kelvin. So don't forget to do that. And we're asked to find, well, what is the new pressure under that new temperature? So we've increased temperature. So remember, this is one of those. So let's write down our unknown here. First of all, unknown is our pressure number 2, our final pressure. And our equation, this is one of those problems where we're looking at the temperature being proportional to the pressure. And so that means we're going to use our relationship of P1 over T1 is equal to P2 over T2. And remember that what we've done is we've increased the temperature. So if we've increased the temperature, chances are our pressure is going to be higher. That's the relationship. So we're expecting a P2 that's higher than 1 ATM. So let's go ahead and plug in some values. So we have 1.00 ATM over the temperature 1, which is 293.15 Kelvin, is equal to pressure 2, which we don't know, over temperature 2, which is 303.15 Kelvin. And so now we can solve by rearranging the equation. We get P2 is equal to, we can send 303 to the other side here, it becomes a multiplication. So 1.00 ATM times 303.15 Kelvin over 293.15 Kelvin. Kelvin crosses out because it's on top and bottom. And so we're basically getting 303.15 divided by 293.15. And we get 1.034112229 ATM. Now, remember that we need to have the correct number of sig figs, so we're going to have our therefore statement. So therefore, the new pressure, P2, is approximately equal to, it looks like we're going to have 3 sig figs in our final answer, so we can round this down to 1.03 ATM. And it did go up, as we predicted. Our temperature went up, and therefore our pressure also went up a little bit, but it still went up nonetheless. So 1.03 ATM. So just like with the other laws, I do want you to watch this quick video. It's a demonstration of Gay-Lussac's law. Draw a label diagram to explain how the law is working. And here you can see some practical applications of it. So this here is a tire with a pressure of 200 kPa. And this is a cold tire. So before you started your journey, before you started your car ride or bike ride or whatever it is, this is a car tire here. But as you use a tire, your tire is warmer. And you'll notice that the pressure is higher as a result of that. So there's a higher temperature here and therefore a higher pressure. And so that's important to understand because when you fill up your tires for bikes or cars, you do have to pay attention to the temperature of your environment. And over here we have an example of a container, which is a pressurized container. So it's under pressure, kind of like the aerosol cans that you might have in your home, the ones that you can kind of spray and a little mist comes out. They're under a high pressure and they tell you to keep away from high temperatures. And it's mainly because of that. If you increase the temperature too much, you're going to increase that pressure a lot. And that could lead the can to essentially exploding, which is not good. You don't want that to happen.